Okay, welcome back, class. So, we will continue our discussion on Lecture 11, FIR Filter Design. So, this is part 2 of our discussion. So, just a quick recap on what we've discussed. Basically, we have an ideal filter at start, ideal filter as constant gain, and a very abrupt change from the pass band to the stop band. And we've made it a physically realizable filter by truncating the impulse response, making it finite duration and shifting it in time. Therefore, we have a practical filter with some ripples in the pass band and stop band and has a transition region or a smoother transition region. And then we can apply some functions, interim functions, so as to make our pass band and stop band have less ripples at the expense of needing a higher order filter to make it more frequency selective. Okay, now we will um, we will now discuss some design of linear phase FIR filters. Okay, so for us to have a linear phase, again, why do you want linear phase? To avoid the distortion on the output waveform. So FIR filters have a desirable property of making the filter have a linear phase. Okay, so IIR doesn't have that ability. Okay, so sometimes we use FIR to take advantage of this ability. So in the first place, what are our conditions on the impulse response for us to have a linear phase? So we have the following conditions. Okay, uh, for a symmetric, we have two kinds of filters. We have symmetric FIR filter. We have the symmetric conditions. H of n is equal to h of m minus 1 minus n. And anti-symmetric basically is just the opposite sign. And when m is odd, we have a center point here at n is equal to m minus 1 over 2. So for example, we are designing a symmetric FIR filter. M is 5, capital M is 5, therefore we have 5 points in our impulse response. We have these conditions. Again, h of n is equal to h of m minus 1 minus n. If m is equal to 5, therefore h of, for example, n is 0, h of 0 should be equal to h of 4, h of 1 is equal to h of 3, and then h of 2 here is our point of symmetry. Because m here is odd, we have a center point. Okay, wherein h of 2 is doesn't have a pair. Okay, it is single. Basically, we have this if m is odd. Okay, we have point of symmetry. Now, if we have these conditions, recall, if we want to get the frequency response, we can do that by just summing for all n, m minus 1, h n, e to the negative j omega n. Right? So, giving us these equations. Okay, h of 0 plus h of 1, e to the minus j omega, etc., etc. Now, we group together so we just manipulate this equation to this one, factoring out e to the minus j2 omega. So we have um, the point of symmetry, the single one, and then we have these pairs. Okay, we can because we want to simplify things here, right? And I think you're getting where this is going. Okay, h of 0 and h of 4 are pairs. They are equal. H of 1 and h of 3 are pairs. And then we can do an Euler's identity here, right? What is recall? Okay, Euler's identity cosine omega is equal to what this is again? Um, something like e to the j omega plus e to the minus j omega over 2. So anyway, basically we have this. Okay, why did it happen? Okay, h of 0, for example, h of 4, we just equate it to h of 0. So we have h of 0 e to the j to omega plus e to the minus j to omega, right? And then just put it here. We have 2 cosine omega, right? Oh, sorry. Right. 2h of 0 cosine of 2 omega. And the same thing here. H of 1 is h of 3. Now, the good thing here is that this function is a real function. Okay? We do not have an imaginary part here, which is denoted by h sub r of omega. Now, what is this term here? This term here is our phase response. Basically, the phase of a real function is 0, right? So, if you want to get theta of omega, we can just add the phases of these two terms. Okay, the phase of this one is negative 2 omega plus 0 degrees. Okay, phi is 0. What is that notation? Theta, phi. Theta is 0 when HR is positive number. But recall, if you have a negative number, the phase that there is pi. Okay, so we have negative 2 omega plus pi. Just review I know complex numbers is very important here. Okay, actually in every engineering subject. So just review if you're not following. Okay, that's all right because complex numbers are really hard to follow, especially when you're not that familiar with that. Okay, so now what is the implication of this one? Theta of omega. We are trying to prove a while ago that these conditions follow symmetry, follow a linear phase. So we have proven actually that theta of omega is a linear phase because this one is linear with respect to our frequency with slope minus 2. So hence we have a linear phase, hence we have a distortion-less filter. Is that the right term? Basically, we do not have distortions in the output because it follows linear phase. Okay, so regardless of adding pi or 0, doesn't change the fact that we have a linear phase. Okay, so actually this one, we can generate some pattern here. Okay, from this equation, h of omega, take note that m is odd here, right? So m is odd. This is the pattern here. Okay, hr of omega is, recall, right? H of 2 is the point of symmetry. So we have here some point of symmetry h of m minus 2. H of m minus 1 over 2. Okay, sorry. H of m minus 1 over 2 plus some 2 multiplied by this function. Okay, recall, right? The first term is h of 0 cosine 2 omega. So h of 0 cosine 2 omega. The next one is 2h of 1 cosine omega. So we have this pattern here. That is when m is odd. Now we do not have time to derive this, but when m is even, okay, recall that when m is even, we do not have this center point, right? So therefore, we just have some summations where hr of omega is this function. Okay, and it actually follows also linear phase, regardless of if m is odd or m is even. Now, we have a asymmetric FIR filter. So the difference here is that, for example, m is 5. We have these conditions. H of 0 is equal to negative h of 4, right? H of 1 is negative h of 3. H of 2 is our point of 0 symmetry but this is equated to 0. Why is that? Okay, each term in h of n has a matching term of opposite sign. Okay, and and basically we must impose that the point of symmetry or the center point should be 0 so as we are still at a linear phase. Okay? Okay, I will not derive that, but basically we have to just remember that when we have an anti-symmetric FIR filter, okay, each term in h of n has a matching term of opposite side, these conditions, and the center point must be 0. That is only for the case when m is odd. If m is even, we do not have a problem. Okay? So, we skip the derivation, but basically we follow the same form. Okay? H of omega is some real function multiplied by this. Okay, so this one is our phase response already. So take note. Okay, we'll just check later. And you could see actually that instead of a cosine, we have a sine here. And actually, we can deduce, it's, recall right, sine omega is, we call this e to the j omega minus e to the over j2. I think this is the formula. Just check, okay, if this is correct. But basically, this one, since we have matching term of opposite sides, right? If we follow this condition, we can actually simplify it to a sine function. Okay? So we can arrive at this. The derivation is very similar for symmetric FIR filter. So somehow we can arrive at a sine function there because we have each term has a matching opposite sign. And we do not have a point. Okay, what do you call this? A center point. That's why we don't have something here. Okay. We equate that to 0 because center point must be 0 when we are designing anti-symmetric FIR filter. Okay. So does it still follow linear phase? Yes, because this is again the phase response. This is equal to negative omega. By the way, you scrap j here. Okay. E to the j theta, the angle of that is equal to theta, so we do not include j. Okay, so negative omega m minus 1 over 2, and then add pi over 2. Okay. When hr of omega is equal to a negative number, we just add pi over 2 to the phase, thereby we have 3 pi over 2 instead. But the main idea here is that we still have a linear phase response with respect to omega. Okay. Okay, let's have an example first. Consider the following ideal filter. Okay, again, this is our ideal filter from negative omega c to omega c. And then we have here absolute value of this one is equal to 1. Okay, so this is 1 e to the minus. We use this so that we still have a linear phase. Okay, so again, the inverse Fourier transform of this one is a sinc function having this formula. And again, this is infinite in duration in general, therefore we truncate it by a filter of length m. Therefore, we have this function already. We have this equation from 0 to m minus 1. We truncated it by m samples. And when n is equal to m minus 1 over 2, okay, we have I think we have a 0 over 0 here, so we need to do L'Hopital's. But when you do that, we have this value. Okay, this one is our Okay, what are we doing here? Uh, this one is our center point. Okay, center point. So, center point is omega c over pi. That is only the case when m is odd, right? When m is odd, we have here a 0 over 0 term. But when m is even, we do not have a problem. So now we observe the following condition. H of n, so for example, h of 0, that is actually equal to h of m minus 1 minus n. So you try it with this function. So for example, m is 31. So we have 30 from 0 to 30, right? So we substitute m is 31 here, and then try h of 0 and h of 30. You should get the same result. H of 0 is h of 30, h of 1 is equal to h of 29, h of 2 is equal to h of 28, etc., etc. Okay. Therefore, the conclusion here is that we have a symmetric FIR filter. Okay. So basically, the ideal filter that we've discussed so far is actually a symmetric FIR filter with order n. Okay? Because it satisfies this condition. And the center point is a constant number. Okay? Okay, so far what we've done is we've started with an ideal filter and then get the impulse response of that to inverse Fourier transform, truncate it or apply a certain window, and then we have a physically realizable filter, right? What if we want to design a filter in such a way that we are able to set some frequency values ourselves? So that is what we call the frequency sampling method. So we want to specify the desired frequency response h of omega at a set of equally spaced frequencies. So for example, if we are designing an m order filter, okay, for example, m is 15, we set 15 frequency points, or actually not necessarily the whole frequency spectrum, no, but just the first half, because we know that in frequency domain we have a symmetry condition to follow. So if m is 15, we are only setting 7 points. Okay. So the first case is alpha. Alpha here is either 0 or alpha is equal to 1/2. When alpha is 0, we are setting frequencies. Omega k is 0, 2 pi over m, 4 pi over m, etc., etc. Okay. So when we do that, we're actually when we specify the desired frequency response, we're actually solving a certain linear equation to be able. We want to solve h of n given h of omega. Okay. So how do we do that? By answering some set of linear equations. So first we define a sub kn is equal to this function. Okay, I'll explain later. Okay, this is very complicated for now, but I'll explain how you solve this. Okay, for a symmetric FIR filter, now this is for the first case. Alpha is 0. Okay, we have this set of linear equations. Okay, m is odd, this one, m is even, this one. The main difference is just the indexing. Okay, but still the same. Still this a sub k, what is a sub kn here is defined by this equation. Okay. So that is for the first case. Now what if we want to design, this is for symmetric FIR filter. Now there is another design here. For example, alpha is 1/2, but we have a symmetric filter. But I do not include this here in the lecture. Okay, but if you want to know further about that, it's very complicated. But we have a design for that. But for okay, you can consult our book if you want to get that. But if we want to have an anti-symmetric filter, this is for the second case. So in this case, we are setting frequency points at these points. Okay, so this case, um, okay, I'll draw it for so it's very clear. In the first case, okay, sorry. In the first case, we are setting these points. Okay. But in the second case, we are not exactly at omega is 0. We are setting at the middle. Okay. So I think you get the point. Basically, when alpha is 0.5, we do not have AHR of 0, but on the halfway point. Okay, and when we have alpha is 0.5, we have the following equation. I just selected alpha is 0.5 when anti-symmetric because the equations are simpler. Okay, but there is also a possibility wherein alpha is 0.5 and you can design a symmetric filter, which we will not discuss. But basically, when we have this, we can design an anti-symmetric FIR filter by the following equations. Now, we haven't actually used these equations yet, but I'll show you how in a simple, because when you have an example, it's easier to understand given a lot of these equations are present. Okay, so for example, we want to design a symmetric FIR filter. M is odd, length is M is 15, and satisfying the following conditions. So if you want to draw the frequency response, for example, this is K. Uh, okay, we have something at 0, right? 0, 1, 2, 3, and then I think this defines the cutoff frequency. Okay, and then 0 elsewhere. Okay, and the rest is just the mirror image of this one. Okay, we are defining here 8 points. Okay, right, 0 to 7. So my mistake a while ago. When M is 15, we are designing 8 points. Now we are following. Okay, this is 8. M minus 1 over 2 plus 1. Okay, that is equal to 8. So we only did 8 equations. Okay, because we have these conditions. To satisfy linear phase or the symmetric FIR filter, we have these conditions. Okay, and then okay, I'll stop. I'll pause here. So when we have this one, um, we are actually at case 1, right? Case 1, alpha is 0, and then we have certain points. We use this equation. A sub kn is equal to this one. Okay, so how do you do that? Okay. What I want you to do is use this formula. Okay, use this formula. How do you... Kasi I want you to define a K by N matrix. Actually, K by N is square matrix because K is equal to N, right? The number of frequency points is equal to the number of points in N. Okay, when we have discrete, we discussed that in discrete Fourier transform. So we have a square matrix A, capital A. So this one, this is a square matrix, K, K by N, right? So again, um, so let me just write the first equation, right? A sub um, 0, 0, h of 0 plus A sub 0, 1, h of 1 plus A 0, 2, h of 2 dot dot dot, that is equal to our first frequency point, which is equal to 1. Okay, so that is our first equation. And then the second equation is a10 h of 0 plus a11 h of 1 plus we have the second equation, which is still 1. K is 1, right? So actually we are getting 8 by 8 linear equations, right? So we have 8 by 8 coefficients of a sub kn. Okay, you can do this in Matlab or any calculator that you have, so that you can actually able to see how to get this. So when you set up this equation, so we have these numbers here. Those numbers can be computed by the equation we have a while ago. 2 cosine, do not memorize it, 2 cosine omega k m minus 1 over 2 minus n. M minus 1 over 2 minus n. And then 1 at the center point. Right? So anyway, we have n by n matrix. We know this. We can solve this one, right? This is what we're trying to get. And through linear algebra, we can solve this by getting this one, this matrix, get the inverse of that, multiply it by these values. These values, again, this is 1, 1, 1, 1, 0, 0.4, 0, 0, 0. You multiply this vector by the set of values that you've computed. Oh, in Matlab, if you really want to do this in Matlab, basically, sorry, paano ako ng slides. But basically, if you want to do this in Matlab, set for n is 1 to n is from 1 to m minus 1 over 2 plus 1, right? But, okay, plus 1. Okay. And then, a of, how do you do this? First set k is from 0 to m minus 1 over 2, right? M minus 1 over 2 plus 1, something, something. And then the first vector is all of this by n. N is the index here. And then you just write the formula. 2 times cosine of omega k. So set just omega k is 2 pi times what you've set k to be, k over capital M. Capital M is 15, right? So 2 cosine, so with omega k times this value. Okay, so basically for loop, this is an n vector matrix, uh, uh, a vector of length n, right? Of length capital K, because we have k points here. Okay. So when we do that, we for loop over n is 1 to m minus 1 over 2. So will become um, a will become 8 by 8, or m by m minus 1 over 2 plus 1 by m minus 1 over 2 plus 1. Okay, and when we get this, we get the inverse of a. So when we define a k n, maybe I'll just send you the code, okay, or just write the code elsewhere. When we want to get h, or sorry, h, we get inverse of a multiplied by h, the h that we've defined. We should get this equation. Okay, it's also a, a, a column vector with 8 points from 0 to m minus 1 over 2 plus 1. Okay, so now we have this, and if we want to get h of 8, h of 9, it just follows the symmetry conditions that we've defined a while ago, which is here. Okay, h of 6 is h of 8. So we just need until 0 to 7. N is 0 to 7. So now, basically that's it, okay? That is for the frequency sampling method. And I will just, maybe I'll just include this in the activity so that you would be able to understand it better, because I know that this is a difficult topic to discuss in a lecture environment, and I'm doing code a while ago, if you could notice, right? So I think it's better if it's okay if you don't understand it right now, but I hope you will understand it better when we code it on ourselves, okay? So just to summarize, basically, why do we want FIR filters? So the main advantage basically of an FIR filter compared to the other filter which we will discuss on the next lecture is its property of having a linear phase response. Again, having a linear phase response would translate to having a distortion-less output. Or basically, we are preserving the shape of the original waveform. Okay? However, the main disadvantage of this filter is that you have to set a high filter order. For example, if you want to satisfy a frequency specification, for example, attenuate 40 decibels at this frequency. So for us to achieve that, you have to set f as a very high number, translating to a large amount of memory. So if you really want a linear phase response, then FIR filter is the choice. But if we want lower memory, then we should try the other design, which is, okay, what is FIR again? FIR is basically short for finite impulse response. Okay, so another good thing about the finite impulse response is that we do not have an issue on stability. Okay, it's always stable because we have a finite duration of impulse response. But the next topic will be the infinite impulse response. So basically, this is an infinite duration impulse response, and we can actually satisfy the same frequency specification with a lower order because we have an infinite duration. But basically, the problem here is the property of it having a linear phase is difficult to achieve. Okay, so IIR in general doesn't have this property, which we love about FIR, right? But the good thing is, since we have an infinite number of samples right now, okay, we can satisfy the same frequency specs with a lower order, lower memory required. But then again, um, you have to take caution on the stability of the filter for the case of IIR. So anyway, we'll discuss that on the next video. So see you there.